All right, everybody. So we're looking at class 67 now. So one of the first things we did as like a do now was looking at noise canceling headphones, how they work exactly, and the main idea here is that they work by using destructive interference. So while the noise canceling headphones hear sound, the ambient sound coming from the outside, they produce their own sound that's an inverted wave to cause destructive interference. And what the wave looks like when the two waves come together is just a flat line, because that's what we would expect to see with destructive interference. For the next part, you needed a ruler to measure the different amplitudes and wavelengths of the different waves. I don't have one on me, and it'll be a little bit different if I do it than yours, so I'll just throw down some numbers that were similar to what some students had. So the amplitude, remember the amplitude is only measuring the distance from equilibrium to the crest or from equilibrium to the trough. Okay, don't measure that total distance, just from the middle line to the crest or the middle line to the trough. In this case, it was about 1.1 centimeters. For the next part, you needed to measure the length of the standing wave. That was the total distance from here all the way to here, not the wavelength. It's the total length of the standing wave. In this case, let's say it was about 10 centimeters. I'm not sure exactly what it was though. Now for the number of waves, you had to realize what a wavelength was. So you basically just count the number of wave cycles. So for example, this would be one wave from here to here. So we have, let's see, 2 waves, 3 waves, 4, 5, 6, 7, 8, and a half. Okay, so it's not just one wave. So what's the length of each wave then? All you would have to do is 10 centimeters divided by 8.5 waves. In that case, getting about 11.18 centimeters is the wavelength, the length of one wave. For the next part, it says the machine making the wave oscillates up and down 12 times in 10 seconds. Calculate the frequency and period. So the frequency is number of oscillations per second. So frequency equals oscillations per second. So it'd be 12 oscillations in 10 seconds, about 1.2 hertz. To get the period is just 1 over the frequency. So remember, frequency equals 1 over period, therefore period equals 1 over frequency. So 1 over 1.2 gives us about 0.83 seconds. So that's how long it takes for one oscillation to occur. The next one, it says an inflatable flamingo is floating in a pool. The waves in the pool move the flamingo up and down 7 times in 4 seconds. How long does it take the flamingo to move up and down 1 time? So we're actually looking for period here. Don't be thrown off, you're not looking for frequency. But to find the period, we have to find the frequency first. So the frequency is equal to 7 oscillations in a span of 4 seconds. So 7 divided by 4 is 1.75 hertz, but that is not the answer. To get the period is 1 over the frequency, so 1 over 1.75 hertz. And we get 0.57 seconds. That's our period and our answer. So again, for these next ones, I don't have a ruler on me, but the answer for the amplitude was about 0.8 centimeters, I think. Again, the amplitude is just from here to here, or from here to here. What's the length of the standing wave? Again, it was about the same, about 10 centimeters, but you might want to check that for yourself. Number of waves, we actually have, let's see, I'll do this in a different color in green. This is one wave, and this is a half wave, so we have 1.5 waves. So how much is a wavelength? It's the total length of 10 divided by the number of waves, 1.5. So wavelength is about 6.7 centimeters. So for frequency, for this next one, frequency is the number of oscillations per time. So we have 8 oscillations in 10 seconds. So your frequency is 0.8 hertz. And our period is going to be 1 over that. which is 1.25 seconds. Again, the next one here, the amplitude was about 0.5, but check that yourself. Again, just either this distance here or this distance here. The length of the total standing wave was again about 10 centimeters. The number of waves, let's see, we'll do that in a different color. We'll go with red. We have 1 wave, 2 waves, 3 waves. So how long was each wave? 10 divided by 3, 3.3 centimeters. If a machine oscillates up and down 10 times, or 24 times rather, in 10 seconds, the frequency is going to be 24 times over 10 seconds, 2.4 hertz. For the period is 1 over the frequency, so the period is equal to 1 over 2.4 hertz. Which is 0.42 seconds. So some of the questions at the end, these are old Regents questions. Also, you can find these on your homework. The time required to produce 1 cycle, that would be the period. That would be choice 3 there. If it were asking about the number of oscillations in 1 second, that would be frequency. Now if we look at the next one here, let's see, there's a lot to this question. It says, base your answer to the questions on the diagram, your knowledge of physics. So it says here, a musician plucks a 0.62 meter long string on an acoustic guitar, and it vibrates with a frequency of 1.96 hertz. On the diagram below, label 1 node and 1 antinode. So the nodes are here, the parts that don't move. So there's a node, and the antinode is right here. Determine the wavelength. So a lot of people had trouble with this one initially because the picture may have been a little too small. Now, yeah, this is 0.62 meters long, and a lot of people thought that was the answer, but realize that this is half of a wavelength. Okay, so if you can kind of picture it, I'll trace it in blue. This is just 1 crest, but then it also will go like this to make 1 full wave. So if you think about it this way, half of a wavelength is 0.62 meters. Therefore, if you multiply both sides by 2, 1 wavelength is equal to 1.24 meters. And that's our answer there. And the last one, a duck floating on a lake oscillates up and down 5 times in 10 seconds. What is the frequency? So frequency is number of oscillations per second, so 5 times in 10 seconds, we get 0.5 hertz.